You are familiar with recursion relations in coefficients, linear recursion relations. So you got a set of coefficients C1, C2, C3, C0, C1, C2 etc. Let us say they satisfy a recursion relation, typically a two-step recursion relation. That is like a second order differential equation, in this case a difference equation, which whose solution can't be written down by inspection. So let us take a typical example. Let us suppose Cn equal to Cn plus 1 plus Cn plus 2 divided by 2, the arithmetic mean of n plus 1 equal to Cn plus Cn plus 2. N is 0, 1, 2, 3 etc. It is a second order difference equation. So to solve it uniquely, I need to specify some initial values. In this case I need to specify two coefficients, C0 and C1, and then the rest of them are all determined by using this recursion relation. The question is, what is the general coefficient Cn in this case? Well, in this case you can guess the answer. What do you think it is going to be? Pardon me? Yeah, it is an arithmetic. So each value is the mean of the values on either side of it. So it must be a linear function, which means it must be of the form an plus b, and then of course you put in C0, C1, you get what a and b are. So it is a very trivial thing. It is the equivalent of a harmonic function in the difference case. Okay. But let us see how to prove this using complex analysis. So the first thing you do is to say that Cn plus 2 plus minus 2 Cn plus 1 plus Cn equal to 0. So C0, C1 are given. That is the recursion relation. And then the next thing to do is to define what is called a generating function, which we will use very extensively in various other contexts as well. So let us define f of z, define this generating function. The generating function as defined as n equal to 0 to infinity Cn z to the power n. So introduce this complex variable z and use your coefficients to multiply z to the power n and define this function of z in this fashion. And then multiply both sides of this equation by z to the power n and sum over n equal to 0 to infinity to get an equation for f of z. What happens then? Well, I have summation n equal to 0 to infinity z to the power n Cn plus 2 plus minus twice summation n equal to 0 to infinity z to the power n Cn plus 1 plus summation n equal to 0 to infinity Cn z to the power n, that is equal to 0 on this side. This is of course f of z itself as it stands. So I replace this by f of z, and what is this equal to? Had this been z to the n plus 1, then I could have said something, but it is z to the power n, so the obvious thing to do is to multiply and divide by a z. So it is 2 over z and then runs from 1 to infinity instead of 0, so it is f of z minus C naught, right. So this is just f of z minus C naught on this side, and ditto here, divide by z squared and you get 1 over z squared f of z minus C naught minus C1z. This whole thing is equal to 0 plus this equal to 0. Okay. So this gives you what f of z is. You can solve for f of z and you get f of z into 1 over z squared minus 2 over z plus 1, and that is equal to, on the right hand side you have C naught plus C1z over z squared minus 2 C naught over z. That is it. So it says f of z equal to, this is 1 minus 2z plus z squared, so it is 1 minus z the whole squared, and on that side you get C naught plus C1 minus 2 C naught z divided by z squared, and the z squared goes away on both sides and you get z minus 1 whole squared. So you give me C0 and C1, I put that in and I discover the generating function is just a rational function, the ratio of two polynomials in Z. But this is a representation of an analytic function, it is a Taylor series here. So what does it imply for Cn? It says Cn equal to the coefficient of f of z of the power z to the power n in the expansion of f of z, okay. It is a Taylor series. So you could write it in several ways. One way is to say that it is the derivative of f of z 1 over n factorial, nth derivative of f of z at that point, but that is a bit of a nuisance trying to find the nth derivative of this function, unless this is 0, in which case it is just a binomial, otherwise it is a nuisance finding it. So you have to find out what the inverse formula here is. This is equal to 1 over n factorial dn over dz to the power n f of z at z equal to 0. There is a better way of finding out what this formula, what this function is, what this quantity is, and what would that be? I want to extract this Cn by an integral formula. What should I do? Remember, when I wanted to extract the pole, I multiplied by powers of z, but now I want to do an integration. I want to integrate f of z times something or the other so as to extract this Cn. I must divide by z, by what power? N plus 1, because this n will go away and give me precisely this coefficient Cn. So you can also write this as equal to 1 over 2 pi I integral around the origin dz over z to the power n plus 1 f of z. So that is an alternative representation. Incidentally, this thing is true for any Laurent series. Even if this had negative powers, this formula is still true, okay, whereas this is not any longer. Once you have a singularity at that point, it is not differentiable at that point. But this formula is true as the inversion formula for even for Laurent series, even when there are negative powers of z or z minus a present, it is still true. And all we have to do is now is to substitute this in here. So it immediately tells you that Cn equal to 1 over 2 pi I integral dz over z minus 1, sorry, z 0, so z to the power n plus 1 around the origin of f of z, which is C0 plus C1 minus 2 C0 z over z minus 1 the whole square. This is the integral we have to do, okay. And now comes the power. I am rushing through this, but we will do this slowly and carefully. You should try this out. What is the integral over? So in the complex plane, you have a pole of order n plus 1, which is here, and you have a contour which encircles that singularity and nothing else, but this function has a singularity somewhere else. Where else is it singular? At z equal to 1. It is singular at z equal to 1. And what sort of singularity does it have at z equal to 1? A double pole, because there is a square here, with some residue, etc. We do not care. The residue will have a contribution from here too, we do not care. So there is a double pole sitting here, and there is a pole of order n plus 1 sitting here, and I hate trying to differentiate a rational function n times. Now if I try to do this integral directly, I need to find the residue at z equal to 0, so I multiply by z to the n plus 1 and then differentiate n times. But I have to differentiate this ridiculous function n times, numerator and denominator, at z equal to 0, which is a tedious task. On the other hand, it would be so nice if all we had to do was to evaluate the residue at this point, because that is just a double pole. I differentiate only once. What should we do? We exploit this rubber band property of this function, and we say, this guy here this is the contour to start with, but I can deform this contour. It is still true, this thing is still true, it is still the same thing. I deform it a little more, make this even bigger, but if you see I can't cross this fellow. So I come here and I keep the sense of the contour very carefully. It is still true, it is still equal to this, and I keep bloating it up, always paying attention to the fact that I can't cross this singularity, till eventually I am guaranteed that that integral is precisely the same here is 1, here is the singularity sitting here as an integral which comes along, does this, goes all the way up arbitrarily far away and goes back and comes down once again, and all the while I keep track of the sense. It is equal to that, and I let this limit become infinite. And what is the contribution due to that? Well, z is some capital R e to the I theta on that line, on that big circle. There is a capital R to the n plus 1 here, there is a capital R there, so let us count those powers. There is an R to the n plus 1, and then there is a capital R from this guy, one more power, and then there is an R squared from this fellow. When these guys cancel and you have an R to the n plus 1, where n is 0, 1, 2, 3, etc. And what happens to this as R tends to infinity? Goes to 0. So this entire contribution disappears. And there are no singularities anywhere on this line. So you can snip this off and these two contributions cancel each other. And you are left with a small circle around z equal to 1, but traversed in the counterclockwise, in the clockwise sense, in the negative sense now. So this thing here is equal to, this whole integral equal to 1 over 2 pi I minus 2 pi I, because it is in the clockwise sense now, times the residue of this function at z equal to 1. But then it means you must take this function, multiply by z minus 1 whole squared and differentiate once, because it is a double pole. So it is 1 factorial times d over dz c naught plus c1 minus 2 c naught z over z to the power n plus 1 evaluated at z equal to 1. And that surely we can do. That is a trivial thing to do. Okay. And then of course you have your expression for Cn, the general coefficient. So you see, you have avoided a whole lot of hard work in this, always the path of least resistance in this case, but you see the power of contour integration. How you are able to convert the integral over this n plus 1th order pole, which involves differentiation n times, to evaluation at the other poles, which is just a double pole at this point. In particular, if C naught is 1 and C1 equal to 2, so you start with 1, 2, etc., then this portion goes away and you just have a 1 here and you differentiate this once. So that gives you a minus n plus 1, the minus signs cancel and you end up with, if C naught equal to 1, C1 equal to 2 implies Cn equal to n plus 1, a linear function in n as we knew all along. Okay. And of course n plus 1 is the arithmetic average of on either side of n plus n on one side and n plus 2 on the other. Okay. So this is a, but you can evaluate this for arbitrary values of C0 and C1 in this case. So solving these linear recursion relations becomes fairly trivial once you know this generating function method, provided you realize that you never try to find the residue at this pole, at this higher order pole directly, but you always open out the contour and pick up the residue from the other poles, and then of course it becomes a straightforward way of doing this. So you might be used to solving these recursion relations by assuming functions for them, assuming answers for them. That is like writing down trial solutions based on superposition of exponentials for ordinary differential equations with constant coefficients, but this is the difference analog of it, but you do not need that. You do not need that. With a generating function you can right away find the exact solution no matter what. So I leave you to find, I am going to give you several exercises. In particular you can amuse yourselves by writing down for this thing Cn plus 2 is Cn plus 1. This is the Fibonacci series. Find out what Cn does in this case. So you have to give me what C0 and C1 are. So typically, for instance, you start with some simple values. So C0 equal to 0, say C1 equal to 1. Find given like this. Incidentally, this Fibonacci series which you are familiar with, where each term is the sum of the preceding two terms, what do you think is the growth of this C as n increases? Do you think it will be a power in n? Clearly the Cn's are increasing with n. The question is, are they increasing like some power of n or something? Suppose you took this Fibonacci series and you try to sum this series to a finite some number of terms by the method of differences. What would happen in this case? Well, you are familiar with the method of differences which you learn in school, right? You have a series and then you take the first difference between the terms, the second difference, and you wait till you get a constant on, right? And from there you work backwards. What happens if you take in the Fibonacci sequence, you take the differences, what do you get? You get the same series over again. You take the next difference, you get the series once again. Now this means that whenever you have taking differences is like differentiating. You have a function which you differentiate and you get the same function back. So what sort of function is it? Exponential. It is an exponential function. It cannot be a power. If I have a function n cubed, function of n cubed, then the next difference will be n squared and then n to the 0. But if I have e to the n, then no matter how many differences you take, it will remain the same thing here. So that is why the method of differences fails for the Fibonacci sequence. And this will immediately tell you that this relation itself tells you that there is no way that Cn is going to increase like any power of n, it is going to increase exponentially fast. And the interesting question to ask is how fast, what is this exponent? So if it goes like e to the lambda n for large n, what is this lambda? That is interesting to find out. So once you find Cn explicitly, of course you will have the answer directly, so I leave you to do this. And what we would like to find out explicitly is a formula for C sub n from which you can read off how fast this exponential growth occurs, right. So the way to do this is to define the generating function. So define f of z equal to summation n equal to 0 to infinity Cn z to the power n, okay, which will converge in some region about the origin, some circle about the origin. We still have to determine this, and this radius of convergence is going to be determined by the properties of this Cn. So we will see in a minute where it converges. Okay. Once you do that, multiply both sides of this by z to the power n and sum from 0 to infinity, and then you of course immediately get since Cn minus plus Cn plus 1 minus Cn plus 2 equal to 0, multiply both sides by z to the n and sum from 0 to infinity, and then you get f of z, that is the first term. The second term is z to the n plus 1 with a 1 over z, and that is f of z minus C naught, of course, because you do not have the 0 term there. So plus 1 over z f of z minus C naught, and the last term is minus 1 over z squared f of z minus C naught minus C1z, and that is equal to 0 on this side. Okay. Multiplying through by z squared, it says f of z times z squared plus z minus 1, that takes care of this portion, and that is equal to on the right hand side you have minus c naught minus c1z, and then this term gives you a plus c naught z, and dividing through by this you immediately get f of z as a rational function, z squared plus z, right, plus z minus 1, that is it. Okay. So the problem is now very simple. In this case it is completely trivial, we do not need to do contour integration because this fellow is after all just as a quadratic function, and all we have to do is to break it up into partial fractions and then use the binomial theorem, and you can compute what the nth coefficient is, this Cn is, but let us do it by contour integration. For arbitrary C0 and C1 you can plug it in and work it out. So this is typically what is going to happen whenever you have a recursion relation with constant coefficients, not n dependent but constant coefficients, then this f of z will typically be some rational function of z, ratio of two polynomials in z, and then all you have to do is to find the coefficient of z to the n in a power series of this rational function about the origin. Okay. So what does this imply? Let us look at the special case C0 is 0, C1 equal to 1 for instance, so that makes life a little easier. This becomes equal to minus z over z squared plus z minus 1. I put C0 equal to 0, C1 equal to 1, okay. And then so Cn, which is the nth derivative of f of z at the origin divided by n factorial, can also be written as 1 over 2 pi I, a contour integral over a small circle round the origin of dz over z to the n plus 1 times f of z, but f of z is now minus z over z squared plus z minus 1. And this is a quadratic function, so it has got two roots, and what are these roots? The roots are alpha beta equal to minus 1 plus or minus square root of this squared plus minus 4 times that, so that is square root of 5 divided by 2. Okay. And what does this whole thing look like? Well, the integrand has an n plus 1 nth order pole because there is a z up there. So it is an nth order pole at the origin, and then there is a pole at root 5 minus 1 over 2 which is somewhere here on this side, that is alpha, and there is a pole at minus 1 minus root 5 over 2, that is here beta. Okay. And the contour looks like this. This is contour C. This is the quantity we have to evaluate. Okay. But like I keep saying, evaluating this residue directly means differentiating this rational function n times at the origin. We do not want to do that. Instead we open this contour out, okay. And as long as you do not cross a singularity by Cauchy's theorem, you can actually open this contour and distort it as you please, provided you are in the region of analyticity of this function. But what is this function like? It is a rational function, it has got a pole here, it has got pole here, pole here, and nothing else, no other singularities anywhere else in the plane. It is actually analytic everywhere else. So you can open this contour out as big as you please. So you can make it really huge like that, provided of course you do not cross that, you go all the way there and you can't cross this and close the contour in this fashion, retaining the sense of the contour. Okay. In principle you could let this radius go to infinity, okay, provided of course the integral still exists, it is finite and so on. You have to worry about the behavior of this function at infinity, but at infinity this is going to go like capital R, the radius of this sphere. This is an r to the n plus 1, so this over this is, there is an r here and r to the n here sitting here, and then there is an r squared sitting here. So the whole thing is actually going to go to 0 as r tends to infinity. Definitely the denominator powers are greater than the numerator powers. One of the things you have to watch out for when you do complex integration is that when you expand this and you look at z at a very large semicircle in either half plane, you have to be careful to remember that this dz itself carries a factor r, because this is r e to the I theta. So there is one power coming from here, and there is an nth power here, and then there is a quadratic thing here. So the whole thing goes to 0 in the limit. Okay. So in principle this is it, this is the same as that, this contour integration is the same as that. But now what happens? Well, all you have to do is to remember that once this is set equal to 0, what is left is this portion which you traversed in this sense and that portion which you traversed here, being careful to go around this integral. So if I can expand this out a little bit, there is a pole here, and what you are doing is coming along, going like this and going back, and these portions cancel each other, there is no singularity at all, but that leaves you with this contour integral. Okay. And exactly the same way, remember the sense, now it is in the positive negative sense that you are traversing this. This too, this integral too came along like this, it came down and it went like this. So this integral, this little circle too is traversed in the negative sense, in the clockwise sense. So there is one more here traversed in the negative sense. This singularity remains where it is. This is at beta, this is at alpha, and it is this. Okay. So what has happened is that this contour integral has become the sum of two contour integrals, one around the point alpha and the other around the point beta, both traversed in the negative sense. So the residue, the answer is minus 2 pi I times the residue at these points. So all we have to do is to say, all we need to do is Cn is 1 over 2 pi I here, and then there is a minus 2 pi I here on this side, okay, and then the function was minus z out there, and then z to the n plus 1. So really there is a minus 1, and then it is the residue at z equal to alpha of the function 1 over z to the n z minus alpha times z minus beta plus the residue at z equal to beta of the same thing, 1 over z minus n z minus alpha z minus. So it is just the sum of these two residues out here in this fashion, okay. And that is easily evaluated because it is simple poles at both alpha and beta, these are simple poles. So what you need to do is to multiply, for instance, the residue at z equal to alpha, multiply this function by z minus alpha and take the limit as z goes to alpha. So it just says remove this factor and set z equal to alpha everywhere else. So this becomes equal to, this cancels out and you get 1 over alpha to the power n, and then this is alpha minus beta, that is this portion, and here you have to set z equal to beta. So you get a beta minus alpha, so the whole thing becomes 1 over alpha to the power n minus 1 over beta to the n, and that is the answer. That is the explicit expression for Cn. All we need to do is to substitute these values, and let us do that and see what happens. So Cn is equal to 1 over alpha to the power n, so that is 2 over root 5 minus 1 to the power n. Oh, there is a 1 over alpha minus, oh there was not this, sorry, this was not there. I have taken that inside. What is alpha minus beta? It is this with a plus sign minus the same thing with a minus sign, so it is just square root of 5. So there is Cn 1 over root 5, and then that is the first term minus beta is this thing with a minus sign, so let us put a minus 1 to the power n, and then it is 2 over root 5 plus 1 to the power n here in this fashion. That is the closed expression. Right. Let us rationalize this. So this becomes 2 over 4 and then root 5 plus 1 goes on top. So it is root 5 plus 1 over 2 to the power n, and then the same thing happens here except root 5 minus 1 goes on top. So root 5 minus 1 root 2 to the power n. That is the expression for Cn. Now we know Cn has to be an integer always. So the square root of 5s must cancel all the way around. For instance, let us just check if C0 was equal to 0. Well, C0, this becomes 1, that becomes 1, it cancels, so C0 is 0 as expected. That works out. C1 is 1 over root 5 and then root 5 plus 1 over 2, and then there is a minus sign here. So it is plus root 5 minus 1 over 2 once again, and it is again equal to 1. 2 root 5 over root 5 is equal to 1. Okay. So that works out, and similarly C2, C3, etc. Once these two work out, it is very sure that the rest of it will be right. Okay. So equal to an integer, that is what is remarkable. For positive integer n, this is equal to an integer, all the square root of 5s etc. cancel out. So what does Cn do at very, very large values of n? So Cn goes like n tends to infinity, goes like an exponential, so there is 1 over root 5 outside, and then this term dominates over that because this is smaller than that, and if you take out this factor, then that ratio tends to 0 as n tends to infinity. So it is really this guy, and this is equal to e to the power n log root 5 plus 1 over 2, but of course root 5 plus 1 over 2 is a very famous number, right. It is the golden mean, right. What is the value of this number? It is 1.618 something something etc. Okay. This guy is like 2.24, so that is 3.24 over 2, this is like 1.62 or so, or 1.618 is the correct, etc. So it increases exponentially. This is a positive number, this log. So it increases exponentially fast, and we know exactly how fast from here. This number, by the way, this root 5 minus 1 over 2, so 0.618 whatever it is, remarkable properties, because you can write it, it is in some sense the most irrational number you can think of. Among all the irrational numbers, it is the most irrational number, because as you know, every number can be written as a decimal which either terminates or recurs, in which case it is rational, or goes on forever without recurring, and then it is irrational, right. You can also write any number as a continued fraction. You can write every number as an integer part plus a fraction, and the fraction can be written as a continued fraction. For instance, you could write a number between 0 and 1, you can always write this number x as equal to 1 over, well, you write 1 over some integer a0 plus 1 over a1 plus 1 over a2 plus 1 over etc. You can keep going like this, where the a's are all positive integers. This is the standard form of writing a continued fraction for a number, right. Now of course, if one of these a's turns out to be much bigger than unity, then you can approximate this continued fraction by truncating it at that point, and those are going to give you rational approximations to any given number. As you know, you can make rational approximations of arbitrary accuracy for any irrational number, and one way to do this would be to either truncate a decimal expansion or a continued fraction expansion. This is how Ramanujan, for instance, found an incredible continued fraction which gave pi to a large number of decimal places. several decimal places. One of these numbers, I do not remember which one, the second or third of these numbers turned out to be 293. That is so large compared to 1 that gave you an extremely good approximation. Okay. Now given that, the more terms you have to keep, the more irrational a number is, if you like, the harder it is to approximate. I mean, the longer you have to go before one of these A's ends up being much larger than 1, it is clear the number in some sense is more irrational, more difficult to approximate by rational. What is the worst case scenario? The worst thing would be if A0, A1, A2 are all equal to 1. If everything is equal to 1, then you don't know where to stop in some sense, right. So you put all these equal to 1, 1, 1, 1, etc. And what is the value of this number? Well, it implies that x is equal to 1 over 1 plus x, which will imply of course that x squared plus x minus 1 equal to 0, but that is precisely the recursion in the quadratic equation we solved. The roots are in fact minus 1 plus or minus square root of 5 over 2. Okay. In this case you want alpha because you want this to be a positive number. This thing is in fact the irrational that I talked about earlier, root 5 minus 1 over 2. Okay. So it is called the golden mean, it has a very large number of interesting properties and so on. We will talk about this continued fraction a little later some other time. Okay. So if you give me any such recursion relation, 2-step recursion relation or 3-step or whatever it is, then in principle you can solve it by using these using the generating function and then inverting it using this trick. So is this clear how we evaluated this integral by stretching it out? Okay.